Okay, so we've been talking about the light-dependent reaction. Now we're going to move into the light-independent reaction. As we said, this is the Calvin-Benson cycle. And I'm using this simulation to kind of help give you a visual or an explanation of what's happening. Now remember, this is a very simplified version, but it gives us a foundation that we can build on. So it gives us something to work with. So let's go ahead and watch this animation of what's happening. So we've got CO2 entering into the cycle. And as CO2 is fixed, we call it carbon fixation, we see that the ATP is converted to ADP, and the NADPH is converted into NADP+. So the electron carrier is dumping his electrons, and the ATP is the energy needed to make this cycle go. So let's take a look at the next animation. And this talks about the recycling of the ADP and the NADP+. And everything goes back to the thylakoids to be recycled, to be regenerated, to be sent back. So nutrients can be recycled, but energy travels one way. And let's look at the production of glucose. So CO2 enters the cycle. Okay. All right, so a couple things have happened here. So for every molecule of CO2 that enters, the cycle must spin 6 times to make 1 molecule of glucose. So in other words, if you had 2 molecules of CO2 enter, then your cycle would have to spin 3 times. And remember, for every spin, you're going to have to produce ATP and NADPH, because these two things kind of make the cycle go round. Now, we're going to kind of switch our screens, or I'm going to try to switch the screen, and we're going to take a look at the Calvin-Benson cycle up close. Okay, so now we have the Calvin-Benson cycle up close, and if you want something to relate this to, this looks like the watch dial that you created in class, because it is very cyclic in nature, and I have pulled out the things that we did see. So let's kind of, we saw the ATP and the NADPH. We also saw the ADP and the NADP+, and of course we saw the ATP on this side, and the CO2. But as you can see, there are things in here that we haven't talked about per the simulation. So let's kind of address those. So the first one is called PGA. The second one is called PGAL, and of course we see this G3P, and then we see the PGAL, and then of course the RUBP. Okay, so what do you need to know about these? These guys, I just call them intermediates. So I'm going to label an intermediate. Oh, sorry. So an intermediate. All right, so it's an intermediate, and I always say that this is a road under construction. So we can't, convert CO2 straight into glucose. We have to go through a process, and the process involves the intermediates. And so this is called phosphoglyceraldehyde. This is called phosphoglyceric acid, phosphoglyceraldehyde, and then G3P, and then we see phosphoglyceraldehyde and the RUBP. So, and I think I would have to look up because I am terrified that I will mispronounce his name. But just to recap, PGA is phosphoglyceric acid, and the PGAL is phosphoglyceraldehyde. As you can see, these names are a mouthful. But then let's talk about this G3P. So this is the basis for glucose. Now for you, the only thing that you need to know is that when the Calvin cycle spins, it makes glucose. I just want to mention the G3P because I don't want there to be any surprises. And of course, when you do take biology 111 or 110 and 111 or 112, these names may come up, and I just don't want you surprised by them. But this is the Calvin-Benson cycle, and as we said, for every 1 molecule of glucose, we need 6 molecules of CO2. Okay, we need 6 molecules of CO2 because it's going to have to fix those carbons. Let's take a look at the chemical reaction real quick that is used for the production of photosynthesis. We got CO2 plus water. Okay, now if you remember, the CO2 is taken in through the stomata. The water is taken up through the roots via capillary action and is split in the light-dependent reaction. And then from these things, we're going to make C6H12O6. And of course, we're going to give off oxygen. That's a byproduct. And with any chemical reaction, I do need to balance. Them. So we need 6 carbons here, and I need 6 hydrogens, and I need 6 oxygens to observe the law of conservation of mass. But this one here, this is the photosynthesis equation. So this is it. So you can see the light-dependent reaction here, and you can see the light-independent reaction here. Remember, oxygen is a byproduct that comes from the splitting of water. So, of course, we're leaving out lots of conversions and lots of steps and lots of processes, but I think this gives you an appreciation for photosynthesis.